Hi folks. Now that we've learned how to draw Lewis dot structures for molecular for molecules, we're going to look at how that arrangement of electrons affects the geometry of the molecules. So this is all about molecule geometry. Molecule geometry is based off of a theory called Vesper Theory. Vesper stands for valence shell electron pair repulsion. And this theory is based around the idea that electrons have a negative charge and therefore electrons repel each other. Electrons try to stay as far apart from each other as much as possible. So electron pairs are going to position themselves as far away from each other as they can to minimize repulsive forces. So in this example here, we have a central atom. These outside atoms orient themselves as far away from each other as they can. And in this example, when there are just two atoms trying to escape each other, the furthest away from each other that they can be is in a straight line. Okay, anything else, they would be closer together, but a straight line, 180 degrees, is as far apart as they can get in this example. So, in order for us to talk about Vesper theory, we need to have definitions for a couple different types of electron pairs, and they're represented here in this water molecule. First of all, you can have bonding pairs of electrons. So this is a bonding pair of electrons. This is a bonding pair of electrons. Those are electrons that participate in a covalent bond. Then you can have lone pairs of electrons. Lone pairs are these non-bonding electrons here. So in this case, for this water molecule, this oxygen has four kind of objects, four things coming off of it. Now, we are going to see that lone pairs repel each other more than bonding pairs do. It's like they take up more space. Lone pairs of electrons take up more space than bonding electrons. Therefore, they reduce the bond angle between atoms. So whenever there are lone pairs of electrons up here, it squishes this bond angle and makes it a little bit smaller. So, if you want to know the shape of a molecule, the first step is to draw the Lewis dot diagram, because you need to know how many bonding electrons there are and how many non-bonding electron pairs there are. Then you count the electron domains that are on the center atom. These are kind of like the objects that are sticking off the central atom. Each lone pair counts as one domain, counts as one object. The thing that's maybe a little tricky is that no matter how many covalent bonds there are to a single atom, one atom means you have one domain. So it doesn't matter if it's a single or double or triple bond to that atom, it counts as one domain. So one bonded atom is one domain. The shape of the molecule is then determined by how many bonding domains there were and how many lone pair domains there were. There are going to be 6 common shapes that you need to know. You should know the shape and you should know the approximate bond angle as well. So, the first shape we're going to look at involves 2 total domains. There are going to be 2 bonding domains, but 0 lone pairs of electrons, 0 non-bonding domains. This is the example that I've already shown you, where these left side and right side electrons are as far apart from each other as they can get in a straight line. And so this is called a linear molecule. This bond angle is 180 degrees. And an example of this would be beryllium dihydride. Beryllium dihydride. This molecule, beryllium, has no lone pairs of electrons on it. It is represented with this Lewis dot structure. So there are no lone pairs there. They're just bonding domains, 1-2 bonding domains off of this center atom. The next shape you need to know about has 3 total domains. Again, all of them are bonding. And this shape is called trigonal planar. It's called planar because this molecule lays totally flat. Right now it's standing up straight, but if you laid it down flat, it would lay flat on the table because it lies in a plane. The bond angles here are 120 degrees. And one example of a molecule that would have the shape is boron trifluoride. Remember, boron is happy with just its 6 valence electrons that it can get from bonding. It doesn't tend to have a full octet. So here boron has its 1, 2, 3, 4, 5, 6 electrons that are caught up in covalent bonds. And of course, I need to finish all these electrons around fluorine. This is the correct Lewis dot structure for boron trifluoride. But this center boron has 1, 2, 3 bonding domains and 0 non-bonding. And this is the shape that it has. Now, this example of a molecule also has 3 objects coming off of the center atom, but this time one of the objects is a non-bonding pair of electrons. Remember, I said these non-bonding pairs take up more space. So when you've got non-bonding electrons here, this angle here isn't quite 120 degrees anymore. It's a little bit less than 120 degrees. So we call this shape bent because when we name the shape, we ignore the lone pairs. We're focused on where are the atoms. Where are the atoms? And this is a bent shape. As I said, the lone pair of electrons squeezes the bond angle, so it's less than 120 degrees now. And sulfur dioxide is an example of a molecule that has this shape. If you have sulfur bonded to 2 oxygens, like so, the sulfur has a lone pair of electrons on the center atom. Oops, I drew too many electrons on this oxygen. There we go. And this is the correct Lewis dot structure for sulfur dioxide. 1, 2 bonding domains for sulfur, plus that 1 non-bonding electron pair. The next shape you need to know about has 4 total bonding domains, or 4 total domains, and all 4 of them are bonding domains. And this is what that would look like. This shape is called a tetrahedron. And although you may think if you divide space into 4 segments that these bond angles should be 90 degrees, they're actually bigger than that, because if you divide into 4 in a 2D area, you can only have 90-degree angles. But if you do it in 3 dimensions, you get the standard bond angle of 109.5 degrees. And an example of a molecule that has this structure would be methane. You could call it carbon tetrahydride. Carbon goes in the middle. Each hydrogen goes around the outside like this. No lone pairs of electrons on the carbon. It has these 4 bonding domains, no non-bonding domains. This is when we get the tetrahedral shape. This shape is called trigonal pyramidal. It's based off of the tetrahedron. It still has 4 total domains, but one of those domains has been replaced with a lone pair of electrons, replaced by a lone pair of electrons. And so the remaining shape just is like this pyramid shape with a triangle base, to this pyramid. That's why we call it trigonal pyramidal, because of the 3-atom base. Now, this lone pair of electrons takes up more space than a bond would, so the remaining atoms get squished closer together. So this bond angle is no longer 109.5. It's been decreased This is actually a 107 degree bond angle. And you don't need to memorize that 107, but you should know that this bond angle is less than 109.5. One example of a molecule that has the shape is ammonia, nitrogen trihydride. Nitrogen goes in the middle, hydrogens go around the outside, and nitrogen has a lone pair of electrons here. 3 bonding domains and 1 non-bonding domain. We have one more shape based off of a tetrahedron, except instead of just having 1 lone pair of electrons here, we have 2 lone pairs of electrons here. So I have 2 bonds and 2 non-bonding domains for a total of 4 domains. We go back to calling this a bent shape. This is a bent shape based off of a tetrahedron, but it's still a bent shape. But this time the bond angle is less than 109.5, so this is kind of more bent than before. And because these lone pair of electrons take up a lot of space, even more space now that there are 2 of them, and the bond angle gets decreased even more. Water is the standard example of a molecule that has this bent shape. Oxygen has a bond to hydrogen and a bond to hydrogen and a lone pair of electrons and a second lone pair of electrons. And this is the correct Lewis dot structure for water. More examples. Here is the Lewis dot structure for phosphorus trifluoride. So thinking about what shape this molecule would have, we have phosphorus, the center atom, has 4 total electron domains. 3 of them are bonding, 1 of them is non-bonding. So this is going to be based off of the tetrahedron structure, but it's not going to be a tetrahedron because we've got this 1 pair of lone electrons here. This is a trigonal pyramidal structure, and the bond angle is 107, less than 109.5. Carbon dioxide. Here is the Lewis dot structure for carbon dioxide. Carbon dioxide, the central carbon has 1, 2 bonding domains, just the 2 bonding domains. If you only have 2 total bonding domains, that is going to be a linear molecule with a bond angle of 180 degrees. Here is a summary of all of those shapes plus a few more, especially for my honor students, for you to know that there are more shapes out there than what we learned. We basically only learned shapes that took us up through having 4 electron domains, but you can have more than 4 electron domains. So yes, so my non-honor students need to know above the line, and my honor students should be aware that more shapes exist. I hope this helped.